All right, welcome back. And today we're going to get into Lecture 8, which is continuing on with sediment transport. And today we're going to start with what we left off with in Lecture 7, which is looking at sediment transport in a mixed bed system. So a stream with kind of a range of different sediment sizes. And so for Lab 4, this is going to be an important part of what you guys do in one of the sections of Lab 4 is to actually calculate the shear stress for a certain size sediment within a kind of a broader size distribution. Okay. And we can do that with this equation, which we call the Komar equation. There are several different other equations out there, but this is kind of one of the simplest. And so what you need to think about when you think about a mixed bed river is how are different sizes of sediment going to be impacted based on the distribution that they're in. So just two examples real quick. So, I mean, consider having, if you have a 10 millimeter piece of gravel, okay, a 1 centimeter piece of gravel, how would that behave if you had it in a bed with much smaller gravel? So say 4 millimeter gravel. So you'd have have a larger grain within a bed of smaller grains. Or on the opposite end of the spectrum, if you had a 10 millimeter gravel in a bed with a predominantly 100 millimeter gravel, how would it behave in that situation with much bigger gravel surrounding it? And so the way that one kind of straightforward way that we can think about this is with a slight modification to the critical shear stress equation that we talked about in Lecture 7. And so this one looks very similar. Okay, we're going to start out with beta, the Shields coefficient or the Shields parameter, gravity, the density of sediment, and the density of water again. But instead of just using the D50 like we do in the classic critical shear stress equation, we're actually going to break out the diameters into the D50 again, like we saw in the original equation, but we're going to take that to the 0.6 power. Okay, so we're going to actually lessen the impact of that in the overall equation. And then we're going to also add in this term at the end here called DI, and we're going to raise DI to the 0.4 power. And so DI is the sediment size of interest, and D50 is the overarching sediment size distribution, or the median grain size of the whole distribution that you're looking at. And so you can kind of rearrange this equation to look at kind of smaller grains within the D50, what their critical shear stress is going to look like, or how the median grain size is going to react within a sediment size distribution with the median grain size, or larger grains within the median grain size distribution. Okay. So again, the components of this are the same as for the original equation. So we have the Shields parameter, okay, again, that we'd get off of something like that table that you saw in Lecture 7, the density of sediment, the density of water, okay. But again, we're going to use the D50 raised to the 0.6 power, and then whatever grain size of interest we want to figure out the critical shear stress for, we'll take that raised to the 0.4 power. And so what that looks like if we graph it is a curve that looks something like this. Okay, so this is this is the curve related to 10 millimeter gravel. So our DI in this case is 10 millimeters. And what I've done here is plotted a range of D50 values. Okay, and so the orange spot right here in the middle, okay, is if we had a 10 millimeter piece of gravel in a grain size distribution with a 10 millimeter D50. Okay, and so if you work that out, it's actually exactly the same as the original equation we had in Lecture 7. Okay, and we get a value of about 7 newtons per meter squared is the critical shear stress needed to move that piece of sediment. So in order to move a 10 millimeter piece of gravel in an overriding distribution with a D50 of 10 millimeters, okay, is about just over 7 newtons per meter squared. Now, the shape of this curve, okay, tells us everything we need to know about this equation, okay, and goes back to what we talked about in lecture 7 about mixed bed rivers, in that if we have smaller stuff in a bigger stream, it's going to be harder to move. But on the flip side, okay, if we actually have larger grains in a smaller grain size distribution, so larger grains within a smaller grain size, we're actually going to need less shear stress to move that than we normally would. Okay, and then on the other side of the dotted line here is that if we have our 10 millimeter gravel in a larger grain size distribution, so you know, in a D50 of 16 here, or a D50 of 64 millimeters here, or if we went all the way up really big, a D50 of 256 millimeters. Okay, so this curve basically shows us that if we have a larger grain in a bunch of smaller grains, it'll be easier to move, and if it's a smaller grain within larger grains, it's going to actually be harder to move. It's going to need more shear stress. Okay, so the Komar equation is giving us basically this blue line here to show us that shear stress can actually change based on the overarching sediment size distribution for our stream. And so that's what you guys are going to be looking at in lab 4. Okay. So let's talk about the different types of sediment transport. So we've got grains moving now. Okay, we've hit a critical shear stress and we've got things moving. Okay, and so there are two main, we call modes of sediment transport. One is what's called the bed load transport. Okay, and so this is where stuff is primarily moving along the bed of the river. Okay, and so if you think back to lecture 7, this is where we have our calculated shear stress either equal to the critical shear stress or greater than the critical shear stress. And so we're basically seeing sand and larger material being moved by kind of rolling or sliding or traction, okay, at that critical, or the shear equals the critical shear. Or we can start to get saltation, like we talked about in lecture 7, when we start to get shear stresses that are greater than our critical shear stress. Okay. So I encourage you guys to download the PowerPoint and actually look at these videos on your own. I'll play them briefly here just to kind of highlight some of the things that are going on, but it's going to be a YouTubeception, where we have YouTube videos being watched on YouTube, so the quality is not going to be great. Okay, I'm actually going to start with the second one. Okay, and so these first couple are actually flume experiments. So in a laboratory flume where they're actually measuring sediment transport in kind of a controlled setting. And so what we're going to look through here is basically an acrylic window looking into a flow here. And so this is a good example of a mixed bed river. There's some larger gravels mixed in with sand. And what you can see is that primarily all of the sediment transport is happening right along the bed of the river. The water up in the top part of the column, the water column here, or in the flow, is actually fairly clear. We don't see a lot of suspended sediment up there. There's not a lot of stuff kind of clouding the water, adding a lot of turbidity. And all of the transport that we're seeing is right along the bed of the river. And so this is a good example of bed load transport. Everything's being transported along the bed of the river. Okay, either saltating or kind of rolling or sliding. Even the little bits of sand are kind of making short hops rather than going up into the flow and actually getting transported a long, long way downstream. Okay, so this next one is a slightly different size distribution, but again, and you can see here is more of a close-up view of some smaller kind of sands and small gravels in with some larger gravels. And so you can see that most of the stuff here is just kind of hopping and sliding. It's not really being sucked downstream a long, long way. And so this is kind of a situation where we're kind of right at the critical shear stress for the larger class and maybe a little bit higher than the critical shear stress for the smaller grains. So the smaller grains are going a little bit further than the bigger grains. And then the last example here is actually kind of a life example. Okay, so this is actually a sand and gravel river in Alaska. And so we're actually going to kind of stick a GoPro underneath the water and be able to see bedload transport kind of out in the field, as it were. Okay, so primarily sand and small gravel here. Okay, and so we're going to go underneath the water. And so here you can see that, again, we don't have a lot of sediment up in the water column. So the turbidity is actually almost none. Okay, the water is very clear. And all of the sediment is just being transported right along the bed of the river. Okay, so all that sand and gravel is just making short hops or sliding along the bed of the river. Okay, so this is a really good example of bedload transport kind of in action in the field. We're not seeing any kind of anything being sucked up into suspension, okay, and everything's just going right along the bed of the river. Okay. So just to kind of go over this diagram that I've been showing a lot lately, okay, is that the kind of those stages of critical shear kind of translate to the two different types of, or two different modes of sediment transport. So the lower end of the critical shear range, okay, we get rolling and sliding. We get slightly higher shear, we start to get saltation. And then once we get way above the critical shear stress threshold, then we start to get up into the what we call suspended load sediment transport. Okay. And so suspended load generally applies to what we call the smaller size fractions, so silts and clays and really fine sands. Okay. And it takes quite a bit of water to get these pieces of sediment kind of up into the flow and moving. But these small the silts and clays tend to stay in suspension for a long time. Okay. And that's, if you look at the critical shear stress for silt and clay, it's actually quite low. Okay. And so lower flows can still transport large amounts of suspended material. You know, the critical shear stress, or the shear stress in a stream has to drop really, really low for things like silt and clay to drop out of suspension. Okay. And usually that means stopping flow altogether is when that stuff will really fall out of suspension. And even some clay minerals and clay material can actually be held in suspension purely through like thermal convection. So if you have, you know, sunlight shining on still water, the amount of thermal energy that's put in can actually cause little thermal circulation currents to kind of exist, and those actually can keep clays suspended indefinitely. So that's really, really small amounts of flow can keep clay in suspension for a long time. And this is why we generally see turbidity kind of extend for a long, long way down rivers. Okay. And then there are situations where flows can have both bed load and suspended load, and that's actually kind of a lot of what we see around the Midwest. Okay, is that we primarily get bed load transport. Most of our rivers, at least in northeast Iowa here, are sand and gravel, and those are primarily transported by bed load. But if you go out and look at the Cedar River, okay, on any given day, there's quite a bit of turbidity in there, so there's also a good portion of suspended load being moved in certain rivers as well. So bed load is one mode, suspended load is another, okay, and very often you will get mixed load as well. Okay, so the next question we want to ask in terms of kind of how this impacts rivers is a question about how and when sediment will be transported. And we've talked about critical shear stress, that we need to get above the critical shear stress in order to transport sediment. But we also need to think about a couple other things, which is primarily the sediment supply. Okay, so how much material is actually getting into the river, okay, and from what sources. So that's kind of a key element in being able to transport sediment, is we need a supply of sediment. Okay, so this is one of the key terms here is sediment supply. So the amount of gravel or the amount of sediment eroded and delivered to the stream from what we call upland sources or the channel margins, so the beds and the banks. So things coming in through kind of overland transport or hill slope processes, and then also things that are kind of already existing right near the channel, okay, or the stream from the beds and the banks. Okay, and so the type and amount of sediment that we can get in a river is kind of is related to the climate of an area, land use in the watershed, the underlying geology. We call the watershed relief, so how much elevation kind of difference we have in the watershed. All of those things kind of contribute to the type and amount of sediment supply that we can find in any given stream. Okay, and it's going to be different for just about every watershed on the planet. Okay, another key term when we're talking about sediment is the capacity, which is how much ability, what's the ability of a stream to actually carry the sediment that is being supplied. Okay, and so this is an important one to think about, is that not every stream has the ability to carry all of the sediment that it's being supplied. Okay, most streams reach an equilibrium with their environment so that they can transport most of the sediment that they're supplied, but capacity is kind of an interesting balancing act that we see kind of tipping one way or the other in a lot of different situations. So capacity is simply the ability for a stream to carry the supplied sediment, and the primary factors influencing capacity are primarily related to hydraulics, so things like discharge, how much discharge, and when that discharge comes, the width of the river, the depth of the river, and ultimately the slope of the river. Okay, because all of those things will kind of play into things like critical shear stress, or the shear stress and critical shear stress for the sediment, and that's important in determining how much capacity a river has. Okay, and the last term is the idea of what we call competence, which is the largest sediment size that can be transported by a typical flow in a stream. Okay, and usually when we talk about competence, we're talking about things like what we call the Q2 or bankful flows, okay, the annual flood, so the kind of peak discharge in a year. Okay, and we usually use those flows because those are essentially the channel forming flows that you guys have read about in some of your readings, is that's when a lot of sediment transport happens. Okay, in a lot of streams, sediment transport isn't happening all the time. It only really happens at the higher end of the kind of flow spectrum for that stream. So competence is related to what size sediment can actually be moved by a typical flow. Okay, so again, this is related to the hydraulics, discharge, width, depth, and slope. Okay. Okay. And so when we think about those ideas of the supply, capacity, and competence, we can kind of combine those in a few different ways and start to kind of understand how different streams actually operate in terms of sediment transport. And so the first type of combination of those is what we call supply limited streams. Okay? And in this case we have a capacity that is much greater than the supply. Okay, so there's more water than available sediment. Okay, and this can happen in a lot of different situations. Okay, this can happen a lot in like bedrock streams, okay, or streams that flow kind of through bedrock canyons. Okay, is that there's a lot of water, but not a lot of available sediment. And so when we talk about these streams, generally we consider them supply limited, in that they could be transporting a lot more sediment, but there's just not that much sediment available. There's not that much sediment being supplied to the stream. Okay, the next is when we have kind of the opposite situation, is what we call transport limited stream. And these are where we see kind of more sediment being supplied to the river than the river has capacity to move. Okay. And this can happen again in a lot of different situations. A key kind of thing that happens out kind of in the world is things like landslides entering stream systems. And so that's where we get, a big dump of sediment into the stream, but the stream may not actually have the capacity to move all of that sediment. And so you can end up with some kind of systems that get out of balance when we have kind of big inputs of sediment through landslides or other mass movements. Okay. Other examples are things like, land use changes, where you're changing the land use in a watershed. You can actually get a lot more sediment being supplied to the river. Okay, so urban development or changes in agriculture, okay, can lead to kind of more sediment being supplied to the river than it can kind of reasonably handle. Okay, another natural situation where we see a lot of transport limited systems is in places that are kind of recently deglaciated. So, glaciers are retreating. So in places like Alaska or Canada, or even in places like New Zealand, these streams are producing some water, but there's a ton of sediment coming out of those mountain valleys. And so we tend to call those transport limited because, again, there's just more sediment than the river can reasonably deal with. Okay. And so generally in a transport limited system, we tend to talk about kind of capacity limited versus competence limited. Okay, so capacity limited is the amount delivered is more than the stream can carry away. Okay, so this is the kind of the landslide example, or the glacier example. Okay, where we get just more, there's more sediment than the river can carry away in a reasonable amount of time. The other aspect of transport limited is competence limited. So streams may not have the ability to transport large sediment away. Okay, and so this, again, happens a lot in mountain streams where we get large pieces of sediment coming into the river. Okay, large cobbles or boulders, get stuck in a river because, maybe it's a small mountain stream and there's just no real way to move that, okay, without a huge, gigantic flood. Okay, and so in cases like this, we do get situations where you can tend to get bed armoring, where you get a lot of large sediment into a smaller stream that isn't meant to be carrying that big that much coarse sediment, and those coarse sediments then armor the bed, like we talked about in lecture 7 a little bit.